Today we're going to look into the tower build project. What we're going to be doing is building a tower that is going to be able to support a weight and making design considerations in relationship to the weight that needs to be supported. So what we're going to have happen is we're going to have 160 pounds come down on top of the tower, pretty much the weight of a common person, and we're going to have it support a 10-pound crosswind. So conceptually, my belief is if you're thinking I'm putting 160 pounds on top of a square entity, that it's just like as if I'm putting 40 pounds on each of the 4 posts, which is accurate, right? Similarly, also with my 10-pound crosswind, I can split that up into 2 5s to be able to move forward. If I break it down into a 2-dimensional setup, it's going to look like this, where I have my 2 40 pounds coming down, my 5 pounds going to the left, and then these arrows down here are called reactionary forces. And so they're holding things into place. This one is a pin support because it's locking down that joint. And this one is a roller support. So all it's doing is supporting that side of the tower from falling. And so it can expand and contract in the heat if need be. And we're not fixing it in there. If we look at it and we draw it in just a sketch, sort of more as a free body diagram, what happens is we lose these diagonal members that are there because they're really just used for tension and not compression. So in this direction, they don't really do anything with that wind. But wind goes both ways, and so we're going to apply that on top of our tower when we build it. We're going to make some assumptions here. We're going to assume that our tension forces are going away from our joints. We're going to assume our compression forces are coming towards it. We're going to have different types of support, which one being a roller for one direction, a pin support for 2 directions. And we're going to say that positive is up and to the right and negative is down and to the left. We're going to have different things that are going on a diagonal be broken into component forces. So if I have this diagonal force, which we'll call K, right, I'm going to be able to say there's a Y component of it and an X component of it for how it works. So to solve this, what we're going to do is we're going to start with a joint that you need the least amount of information for. And so that's the one that has the most numbers on it typically. So we're going to probably start here or here, right? The compression and the tension is going to be consistent in the member. So if we're pushing up here on this member up to that 40, we're also going to be pushing down here with 40 onto that member. You'll see that further in a second. I think it's useful to develop a document that looks like this. I have a small reference sketch of where everything is going, and then I have pages set up to where I can address each of the different joints individually. And so, now if I look at it, a moment ago I said we're going to use one of the largest numbers, which more the most numbers for our start. But if we sit here and we look at this point this joint H, it actually, while it only has one number, there's more information actually applied. And so if I sit here and I have 40 pounds going downward, right, all my Y forces need to sum when I add them together equals 0, and all my X forces also need to be going to 0. And so if I sit there and I say, hey, I have 40 pounds going down, what could cancel it out? Well, 40 pounds going up, right? And if I have those two together, that makes sense for that math. I also know there's no horizontal force, so my member GH must be 0. Now, I will say that when we go into our next one, we carry that GH in. So we found that the GH here for that member is 0, right? And we started on this document. But whenever we have these, we're sort of making an error here, because typically when you have forces in a free body diagram, and they're considered forces, we want them to actually have an arrowhead on them. But I've left them off so that I can sort of bring them in as we go. So now what I have is I've got a horizontal force here. I've got a horizontal force of GH, and then I have the X component of FG here. And I get FG because it's the between F and G, that's the member. And then, so that's going to be pulling, because what I've got is my 5 pounds can only be canceled out by the 5 pounds on this FG, right? But if this one's pulling this way, it's also going to be pulling down, working against EG, which is going to be working up. And so, I'm going to break that up. Right? I'm going to have those 2 members there for me. I'm going to go ahead and solve for those. So I'm going to find that my, if I say, hey, it's got to have 5 pounds of force to cancel out that 5 pounds of force, I'm going to know that my hypotenuse, when I calculate, it's going to be 6.4, and my vertical component is going to be 4. I can then apply those, because again, this is just a triangle. into our equation. So this yellow is represented by both the gray, so I really am not doing calculations with it anymore after it's solved. But when I'm seeing here, my horizontals, when I sum all those, I've got -5 and 5, which equals 0. And then my verticals, I've got -40 and -4 and EG, which is just written right here. And if I add those together, I know that I have to be coming up with 44. Similarly, when I've got this calculation, I know that, again, we've got component forces of 5 and 4. The reason is because it's within a square, right? And so the angle is going to remain the same. The diagonal force is remaining the same. And so I can put those values in directly. And so I know that I have a horizontal force here that's -5, and I only have one option to cancel it out, which is EF. So I know that EF is going to have to be pushing back towards this direction. I also see that my 40 going down is canceled out by this 4, right? So 40 minus 4 is going to equal my 36. And so it will end up looking like this, where we have 3 compression forces and 1 tension force going into that joint. So if we were to sit there and solve the rest of this, right, what we would want to do is solve for joints E, D, C, B, and A, right? And then what we'll have is we'll be able to check our math with our external forces. So if I add my 2 vertical forces here, they will add up to be whatever these 2 vertical forces are here that are from our supports, or reactionary forces. And so they're not going to be 40 and 40, but they might be 60 and 20 or something like that. We will know this right here will end up being 5. And so we're able to sort of move forward with that as a check. And so go through, work through the problems, see what else you can solve, and make sure that you're able to get that check with the external forces.